Welcome aboard, fellow enthusiasts, as we embark on another incredible video. It's a pleasure to have you join us as we uncover the secrets of air changes per hour. Air changes per hour, abbreviated ACPH or ACH, or air change rate, is the number of times that the total air volume in a room or space is completely removed and replaced in an hour. If the air in the space is either uniform or perfectly mixed, air changes per hour is a measure of how many times the air within a defined space is replaced each hour. Perfectly mixed air refers to a theoretical condition where supply air is instantly and uniformly mixed with the air already present in a space, so that conditions such as age of air and concentration of pollutants are spatially uniform. In many air distribution arrangements, air is neither uniform nor perfectly mixed. The actual percentage of an enclosure's air which is exchanged in a period depends on the airflow efficiency of the enclosure and the methods used to ventilate it. These systems range from a conceptual system of perfect displacement, which removes and replaces all air in a space, to a short-circuit flow in which very little of the existing air is replaced. The actual amount of air change in a well-mixed ventilation scenario will be 63.2% after 1 hour and 1 ACH. In order to achieve equilibrium pressure, the amount of return air leaving the space and the amount of supply air entering the space must be the same. Let's now zoom in on air changes per hour and uncover the hidden gems that lie within. In imperial units, quad ACPH of Rakakov, where EACF equal number of air changes per hour, higher values correspond to more ventilation. Q equal volumetric flow rate of air in cubic feet per minute. Vol equal space volume LWH in cubic feet. In metric units, quad ACPH of Rakakov, where EACF equal number of air changes per hour, higher values correspond to more ventilation. Q equal volumetric flow rate of air in liters per second. Vol equal space volume LWH in cubic meters. For a given room or building size and number of air changes per hour, the volumetric flow requirement is usually specified in cubic meters per hour when using metric units. Now, let's shift our perspective and explore ventilation rates through a fresh lens, unlocking new perspectives. Ventilation rates are often expressed as a volume rate per person, CFM per person, Ls per person. The conversion between air changes per hour and ventilation rate per person is as follows. Quadruple frackt, where P equal ventilation rate per person cubic feet per minute, CFM per person, or cubic meters per minute per person. ACPH equal air changes per hour. D equal occupant density square feet per occupant or square meters per occupant. H equals ceiling height feet or meters. 1 cubic meter per minute equals 16.67 liter second. Moving forward, we'll be taking a closer look at air change rate recommendations. Air change rates are often used as rules of thumb in ventilation design. However, they are seldom used as the actual basis of design or calculation. For example, residential ventilation rates are calculated based on area of the residence and number of occupants. Non-residential ventilation rates are based on floor area and number of occupants, or a calculated dilution of known contaminants. Hospital design standards use air changes per hour. Recommended air changes rates can be found in relevant standards. Recent research indicates that air changes per hour ACH alone may not be a reliable parameter for making ventilation recommendations. A new parameter, effective air changes per hour, called ACHH by Motobazabihi et al., which incorporates both the flow rate and large-scale airflow patterns, could provide a more accurate measure of how efficiently air is supplied and circulated within a room. This is particularly important for effectively managing airborne disease spread. Let's now turn our gaze towards methods of measurement and explore the fascinating connections it has to offer. Air changes per hour is a measurement intended to communicate the air change effectiveness of a space's ventilation system. Discussion around the ASHRA Standard 62, ventilation for acceptable indoor air quality, led to the development of a more direct method of measuring air change effectiveness with the use of a tracer gas. A tracer gas is a small amount of easily detected gas which is mixed with air in order to study airflow patterns. This method directly compares the age of the air where occupants breathe to the age of air that would occur were the air of the space perfectly mixed. The method is designed to more accurately understand the effects of airflow patterns within a space, to identify or avoid such occurrences as short-circuiting airflow patterns, in which most of the supply air goes directly to the exhaust and fails to mix with the air already present. There are two ways to apply this method. The most commonly used technique, tracer gas decay step down, consists of a short burst of gas injected into the space to establish a constant concentration within the building. Then injection is stopped and concentration decay at a certain position is recorded. And second, tracer gas step up, where tracer gas is injected at a constant rate and the concentration response at a certain position is recorded. Now, we shift our focus to airtightness in building, a topic that deserves our attention. The most common technique to measure airtightness is the fan pressurization method, also known as the blower door test. It is measured by the number of air changes per hour ACPH that occur when there is a differential pressure of 50 pascals between outside and inside the building. If an air volume equal to the inside volume of the building flows across the envelope in 1 hour, then ACPH 1. Airtightness improves buildings' energy performance since low airtightness levels imply high infiltration rates, drafts, risk of condensation, and moisture accumulation, and other effects. For this reason, the Passive House Standard established performance requirements for airtightness requiring be less than 0.6 ACPH with a pressure difference between inside and outside of 50 Pa. It is worth noting that ACPH measured with the blower door test at a differential pressure of 50 pascals mimics the situation of a sustained 20 miles per hour 32 km wind outside. The natural air leakage, under calmer conditions, is likely to be much less. As a result, the so-called natural ACPH may be a factor of 10-25 times smaller. This is of relevance since high-performance building methodologies strive to keep ACPH low under standardized, weather-stressed conditions, while air quality considerations may require sufficiently high natural ACPH. In the next portion, we'll be immersing ourselves in the realm of effects of ACPH due to forced ventilation in a dwelling and examining its broader implications. Forced ventilation to increase ACPH becomes a necessity to maintain acceptable air quality as occupants become reluctant to open windows due to behavioral changes such as keeping windows closed for security. Air changes are often cited as a means of preventing condensation in houses with forced ventilation systems, often rated ACPH though without referencing the size of the house. However, where ACPH is already greater than 0.75, a forced ventilation system is unlikely to be of use at controlling condensation, and instead insulation or heating are better remedies. 7 out of 8 houses studied in NZ in 2010 had an ACPH corrected for ventilation factors of 0.75 or greater. The presence of forced ventilation systems has been shown in some cases to actually increase the humidity rather than lower it. By displacing air inside a dwelling with infiltrated air brought in from outside the dwelling, positive pressure ventilation systems can increase heating in winter or cooling in summer requirements in a house. For example, to maintain 15°C temperature in a certain dwelling, about 3 kg of heating are required at 0 ACPH. No heat loss due to warmed air leaving the dwelling. Instead, heat is lost due to conduction or radiation. 3.8 kg at 1 ACPH and 4.5 kg are required at 2 ACPH. The use of roof space for heating or cooling was seen as ineffectual, with the maximum heating benefits occurring in winter in more southerly regions, being close to the South Pole in these southern hemisphere reports, but being equivalent only to about 0.5 kg, or the heating provided by about 5 100W incandescent light bulbs. Cooling effects in summer were similarly small and were more pronounced for more northerly homes being closer to the equator. In all cases, the values assumed that the ventilation system automatically disengaged when the infiltrating air was warmer or cooler as appropriate than the air already in the dwelling, as it would otherwise exacerbate the undesirable conditions in the house. I love interacting with my viewers, so leave me a comment and I'll do my best to respond.